Okay, so in this video we're going to talk about enthalpy as related to phase change. So hopefully you remember that enthalpy is a change in the heat of a substance or for a reaction. We're going to apply the same idea to how phase change occurs. So first let's review a little bit about enthalpy. Enthalpy is symbolized by the capital H, and normally we see it as delta H, or change in enthalpy, because we can only see the change in enthalpy or heat coming into or leaving a system or process. Alright, so if we look at the two graphs, the graph on the left represents a change that would be exothermic. And so exothermic means we have a net loss in heat. So in our graph, we have our enthalpy of our reactants, or our starting material, and then our enthalpy of our products, or our ending material. And we can see that overall we have a change in delta H where we have a loss of energy, or a loss of heat. So this tells us that our ending product has less enthalpy than what we started with. So if we think about this in terms of phase change, we're looking at our initial phase as our reactants or starting position, and our final phase as our products or ending position. And we want to look at how much heat is captured in each of those phases. So if we're losing heat, that would be an exothermic change. If on the other hand, we have more enthalpy in our ending material or final phase than we do from where we started, that would be an endothermic change, or an increase in total enthalpy for the process or the system. Alright, so make sure you remember that delta H negative is associated with exothermic, and delta H positive is an endothermic change. Alright, so if we look at how this applies to phase change, there are constant values denoted as enthalpy values, or change in heat values. So the enthalpy of vaporization, delta H of vaporization, is a constant value that represents the heat required to vaporize 1 mole of a liquid into a gas at constant temperature. Alright, so we can look up tables of these values for different substances. Here's our delta H of vaporization, and this is energy units per mole, so kilojoules per mole. And we can see that for substances that have greater intermolecular forces, like our ammonia, which has hydrogen bonding, HCl, which is a strong dipole, so dipole-dipole forces, have higher delta H of vaporization. If we get a weaker intermolecular force, we get lower values of delta H vaporization. It takes less energy to convert those from liquid to gas. But remember, size matters for our intermolecular forces. So CCl4 is nonpolar, but it's fairly large, so we have a large delta H. However, water is higher because water can form hydrogen bonds. If we look at the last one, NaCl, what type of intermolecular forces are these? This is just an ionic compound. So electrostatic attraction between ions creates a lot of energy requirement to vaporize. So we have a very high delta H of vaporization. Now delta H of fusion is a similar idea. Instead of vaporizing from liquid to gas, fusion is melting from solid to liquid, but it's the same idea. And we can see that this is also correlated with the strength of the intermolecular force. The stronger the intermolecular forces, the greater the delta H value is going to be. So vaporization and fusion are both endothermic processes, which means we have a net increase in energy, or net increase in heat. And if you think about this, it makes sense. If I want to vaporize a liquid, I want to turn liquid into a gas, do I need to heat it up, or do I need to remove heat? So if you think about it, in order to turn liquid water into a gas, we would heat it up. right? We would increase the temperature and it would start to vaporize. So we have a net increase in energy, so that's endothermic. Melting is the same way. If I want to melt a block of ice, I need to heat it up. So endothermic processes. There is a third endothermic process. So we have vaporization going from liquid to gas. We have fusion going from solid to liquid. And our third process would be going from solid directly to gas. Alright, our solid directly to gas, our sublimation, is also endothermic. The other three phase changes will be exothermic, going in the opposite direction. If I want to condense a gas back into a liquid, I need to remove heat from it, so net loss of heat is exothermic. If I want to freeze a liquid into a solid, I need to remove heat from it, so exothermic. And then a gas going directly to solid, deposition, I need to remove heat. So all three of those are exothermic changes. Alright, so our heat of fusion, or enthalpy of fusion, delta H fusion, is our endothermic process. So just like enthalpy of vaporization, it will be a positive value. It changes slightly with temperature, not huge changes. And it is the opposite of our crystallization or freezing. Alright, so for our enthalpy values, the endothermic values are positive, the exothermic values are negative. But for opposite processes, like fusion and freezing, they have the same numerical value, only differing by a negative sign. Alright? And we'll look at that again. Delta H of vaporization is normally the largest of the enthalpy values for phase change, because it takes the greatest amount of energy to go from a liquid to a gas state. We not only have to loosen the intermolecular forces, they get broken completely. Gas molecules are no longer interacting at all. So that takes a greater amount of energy. If we're only melting or fusion, we just have to loosen up the intermolecular forces. So it takes less energy than vaporization does. Now, enthalpy of sublimation is the summation of the fusion and the vaporization values. So if I want to start at a solid, melt it into a liquid, I would need my delta H of fusion, then vaporize that liquid into a gas, my delta H of vaporization. I have the same energy requirement as if I had gone from solid directly to gas with my sublimation. So if I know fusion and vaporization values, I can calculate sublimation values. The table below shows a few delta H of fusion values. Based on what the type of liquid is, we can see how the intermolecular forces plays a role. So water having hydrogen bonding has fairly high delta H of fusion. Isopropyl alcohol, still hydrogen bonding capable, but a little less than water can because it's a larger molecule. Slightly smaller. Acetone, polar, quite large hydrophobic areas. And then diethyl ether, slightly polar, even larger hydrophobic areas, so a higher delta H of fusion. Alright, so if we look at the triangle for our enthalpy change, we have 6 different phase changes: sublimation, deposition, vaporization, condensation, fusion, and freezing. If we add in now our enthalpy values, our endothermic values, delta H of vaporization, delta H of fusion, and delta H of sublimation, are endothermic values, positive delta H values. These are really the only scientific values that are given a name that you can search tables for. Their inverse processes, such as enthalpy of deposition, enthalpy of freezing, and enthalpy of condensation, are not actual science values, and you can't really find tables of these. what you find is just the opposite process value, and you put a negative sign on it. So our enthalpy of condensation is really just the negative enthalpy of vaporization value. And the same is true for the others. Enthalpy of freezing is just the negative enthalpy of fusion. Enthalpy of deposition is the negative enthalpy of sublimation. Alright, so if we look at the 3 endothermic processes and the 3 exothermic processes, and remember that it's additive, alright, so our sublimation value is just our fusion plus our vaporization value. And if we look at the opposite, deposition would just be freezing plus condensation values. And remember, our endothermic values are positive, our exothermic values are negative. Alright, this is the concept behind our phase change and enthalpy. If you look to other videos, it will talk about how to do the math.